Hello and welcome to the Edexcel Further Maths videos for Mechanics 1. This is the second video in the Elastic Springs and Strings section, 1.2 Elastic Potential Energy. So we've already discussed previously the energy stored in the form of gravitational potential energy, but if we've got a spring that's been stretched or compressed, we've got energy stored in the spring, and that energy is going to be released when the spring is released. If you think of it like if you have a bungee jumper, when they jump off, as they reach the bottom, we've got a lot of potential energy in that string, and that's what pulls them back up again. And we refer to this energy stored as elastic potential energy. So when we've got a spring that's stretched, work is done in stretching that spring. And we saw earlier in a previous video that for a variable force, the work done is the integral between x1 and x2 of the force with respect to x. Now the same applies to strings. So we've got from Hooke's law that F is lambda x over L. And if we use that with this work done formula, we have that the work done in doing the extension from 0 to x, lambda x over L dx. And if we do that integration, we find that the work done is lambda x squared over 2L, where lambda is the modulus of elasticity, x is the extension in the string, and L is the natural length of the spring or string. So that work done in doing that stretching isn't wasted, it's stored in the spring, and we call that elastic potential energy. And we can say, because of the work energy principle, that the elastic potential energy is equal to the work done. So the elastic potential energy is equal to the work done, which is lambda x squared over 2L. We treat this very similarly to gravitational potential energy, and we include it in our energy calculations. And in some situations, we may be using both elastic potential energy and gravitational potential energy, and in fact, kinetic energy as well. So let's have a look at this first example. We've got an elastic string of natural length 1.5 meters and modulus of elasticity 50 newtons, and it's stretched to a length of 2 meters. Find the energy stored in the string. So we know that the energy stored in the string is the same as the work done. So the elastic potential energy is lambda times x squared over 2L. In this particular case, lambda is 50, L is 1.5, and x is 0.5. So if we substitute these values in, we have 50 times 0.5 squared divided by 3. So we get an elastic potential energy of 4.17 joules. Okay, so here now we have an object attached to one end of a light spring, natural length 40 centimeters, and modulus of elasticity 180 newtons. The other end is attached to this fixed point O, and it's pulled away to a distance of 55 centimeters. So we know that the natural length of the spring is 40 centimeters, and it's been extended to 55, so our extension is 15 centimeters. It's a smooth table, which means we don't have any friction. In later videos, we will be looking at what happens when we have friction as well. So we're trying to find the work done. Work done and elastic potential energy are the same. So the work done is lambda x squared over 2L. We worked out that x is 0.15. So our work done is 180 times 0.15 all over 2 times 0.4. You'll notice I've put all these lengths into meters. So we find that the work done in stretching that string to a distance of 55 centimeters is 5.06 joules. So that means it's the work done, and that we also have elastic potential energy now stored in that spring of the same value. There's a slightly neater version for you. Okay, thanks for watching the second video in this series, which was elastic potential energy. Next time it will be 1.3, problems using conservation of energy.